Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Now, if you want to study a manifold locally at any point, you can look at the tangent space there. If you want to study a Lie group, you might want to try to do something similar, because essentially what's a Lie group? A Lie group is just a smooth manifold with a compatible group structure. So that raises the question, suppose you want to study the group structure locally at a point of a Lie group. Okay, how can you do that? Well, it turns out that what you can do is you can put some extra algebra structure on that tangent space, and that extra algebra structure is called the Lie algebra, and that is the topic of this video here. Okay, so to set our notation, we're going to let G be our Lie group, and this Gothic G here is going to be the tangent space at the identity to that Lie group. So remember, we looked at these this tangent space here, G, and for every vector inside here, we saw that you could smear this out to give you a left invariant vector field on the whole of G. And I'll denote that left invariant vector field with X subscript V. So the first thing I want to define is what's called the universal enveloping algebra. So this object here is in some ways a more fundamental object when we want to study Lie groups. It's going to be denoted by U of this Gothic G. And what is this universal enveloping algebra, U of G of this G? Well, basically it's just the R algebra that's generated by all the differential operators associated to these XVs. So remember, these are vector fields. They give you differential operators. They can be used to differentiate smooth functions on G. And you look at the algebra that they generate. So that's the definition part. And what's the proposition part? Well, it turns out that this algebra here is precisely the set of all left invariant differential operators on G. So certainly if you take some of these differential operators XV, okay, and you compose them together and you add them together, since these are each left invariant, okay, the algebra generated by them gives you left invariant differential operators, but it turns out that there are no others. All of them can be generated in this fashion. So I won't go through why this is true. It's actually not too difficult, but I will do a little example, and hopefully you can see kind of where this comes from. Okay, so let's have a look and see what's going on here. Okay, so we've got the Lie group G here is just the Euclidean group, n-dimensional Euclidean space. Okay, so with coordinates x1 up to xn, and let's give it a basis e1 up to en. Okay, so the identity here is just a 0, so you can look at the tangent space there. Of course, it's just the same vector space. Okay, but we'll write it with the EIs as a basis, so it's the direct sum of all the EIs, R times the EIs. Okay, and then what are the associated vector fields to this? Okay, so if you have this standard basis vector EI, then what is the corresponding vector field? I'll write down the differential operator instead. It's just partial differentiation with respect to xi. Okay, so they're your differential operators. Okay, so your general element inside here, if you want to think about it as a differential operator, are just R linear combinations, okay, of these partial derivatives. Okay, and that's what you have. And what you can do is these R linear combinations of these partial derivatives, you can compose them together to get higher order differential operators. You can add them together, and if you look at the algebra that's generated by them, of course, what do you get? Well, by composing them with each other, of course, all you'll get are just your mixed partial derivatives like this. And then if you look at the set of all R linear combinations of these, then of course you get something which is closed under composition or multiplication, and also because you're taking the R linear combination closed under the vector space operations as well. So that means that you get the whole of this universal enveloping algebra of this, what we'll call the Lie algebra. Okay. So another way of thinking about this object here is it's just a set of all constant coefficient differential operators. And if you look at this viewpoint, it really suggests to you that it is indeed the set of all left invariant differential operators. Because if you didn't have constant coefficients, that means that when you look at the differential operator at one point, okay, compared to another point, then it can act differently on the functions. Okay, so you want this to be constant coefficient because these are left invariant. Okay, so that argument gives you the equivalence of the two descriptions of the universal enveloping algebra that's given in this proposition definition here. Okay, so I hope you can see that from this argument here, actually, it's very easy to give a set of generators for this universal enveloping algebra. You just need a basis for this G, okay, a basis for this tangent space. But the natural question now is, what are the set of relations? And that's actually a very, very interesting question. Okay, and to tell you what the relations are, I have to introduce firstly the notion of the Lie bracket. And that's quite a general sort of a notion that you can talk about. And the general setting of it involves a smooth manifold, let's call it M, and two smooth vector fields X and Y. And being two smooth vector fields, you can talk about the corresponding differential operators, let's call it dx and dy. Now for these differential operators, they happen to be to commute with each other. And in fact, if you think about it a little bit, actually, what is this algebra here? Okay, this algebra is actually just a polynomial algebra over R, so with coefficients in R, in which generators? In these generators here. These all commute with each other, okay, because you can reverse the order in which you do this partial derivative. But in general, with differential operators, they don't commute, okay? So if you look at an expression like this, dx dy minus dy dx, this is initially a second order differential operator, okay? This is, on the face of it, you know its order is at most 2, okay? So it looks like it's a second order differential operator. But strangely enough, it's actually a first order differential operator. It's a first order differential operator associated to a certain vector field, and we denote that vector field by x bracket y, and this is called the Lie bracket of x and y. Okay, so this is a rather beautiful sort of more an observation than anything else. Okay, and to see why it's true, it's not too difficult. But the key calculation occurs when M is just a Euclidean space. You can reduce to a general manifold from a general manifold to the Euclidean case, and the easiest to write down is when M equals R. Otherwise, the notation gets a little bit heavy. So let's just do the case when M equals R, and then you'll see at least all the ingredients as to why this ought to be true. Okay, and that will be clear already. Okay, so you're thinking of a vector field on R. So this is the type of thing that you imagine when you write it down. Okay, so basically, what is the vector field here? So at every point, you essentially just have to give the multiple of d dx. Okay, so x may be f of x times d dx, and similarly y may be g of x times d dx. Okay, so they're two general sorts of differential operators associated with vector fields on the real line. So let's do the first calculation. Okay, let's apply the two differential operators dy and then dx to some function p of x. Let's just see what that is. So if we apply dy to p of x, of course, you just differentiate p to get dp dx and multiply by g. That's the first part. And the next thing you do is you apply dx. Okay, so that means you differentiate this here and then multiply by f of x. So the multiply by f of x is easy enough. And then to differentiate this, you use the product rule. Okay, so you use a product rule. So firstly, you can differentiate this g term. You get dg dx and you multiply by the dp dx. And then you can also leave the g of x and multiply, differentiate the dp dx term. Okay, and oh, I've lost the g of x here. Okay, and as you can see, this composite here is definitely a second order differential operator. There's a 2p dx squared, okay, and there's also a portion which is involves the d dx. Not only do you take a second derivative of p, you also take a first derivative of p, and then there's some coefficients which are polynomials which come out the front as well. Okay, so we can swap the order of x and y, so that means you just swap the f and g, okay? So this f becomes g, okay? So instead of g dx dp dx, you get df dx dp dx, and instead of this g of x d2p dx squared, you get f of x d2p dx squared. And there's a plus there. And so what happens now? So what we want to do is we want to subtract these two, right? We want the difference of this. Because this in some ways, this Lie bracket measures the failure of commutativity. Okay, if this is 0, that means the differential operators dx and dy commute. However, looking at its difference, if it doesn't, of course, vanish, then this means that this dx and dy, they don't commute. Okay, so this is the failure of commutativity, which and this difference here is used a lot in mathematics. And what we find is when we look at the difference, let's look at the second order terms. You've got an f of x g of x times d2p dx squared minus a g of x f of x times d2p dx squared. So they cancel out. Okay, and that's the key thing. Even if you have higher dimensional Euclidean space, okay, the key point is that the second order terms, when you look at this difference, they cancel out. And you're just left with first order terms. Okay, so let's look at the first order terms and see what we get. So, so you differentiate p, and then you multiply by f of x dg dx, f of x dg dx. And here, this first order term, you differentiate p, and you multiply on the left by g of x df dx. So you're subtracting this one, so you subtract df of x times g of x. So it turns out that this dx dy minus dy dx is just this polynomial times d dx. So it's this differential operator, okay? And it's associated to this vector field here, because this is just a smooth function times d dx. And that establishes this fact in the case when m equals r, and it's representative of the general proof. Okay, so now what we want to do is we want to put an extra algebra structure on this G, the tangent space to G at 1. And that algebra structure is going to be called a Lie algebra structure. Okay, so let's see what's involved. So remember, this is a vector space. What we want to do is impose a type of multiplication on two elements A, B inside here. So firstly, since you have this A, B inside this G, you have corresponding left invariant vector fields XA and XB. You can also take their Lie bracket, and that will be another vector field. And since this vector field is composed of left invariant vector fields, okay, it's just the difference between the two composites in either order. That's also going to be left invariant as well. And so since that's left invariant, it's natural to think of the corresponding element at 1. Okay, what is its value at 1? So that's an element of the Lie group, and that is denoted A bracket B, and that's the Lie bracket of A and B. In other words, what you do is you look at this left invariant vector field, okay, and you just evaluate that at 1. Look at what's the corresponding vector at 1, and that's going to be the Lie bracket of A and B. And what is the Lie algebra of the Lie group G? Okay, it's this vector space Gothic G here, so this tangent space at the identity, which is a vector space, it has this vector space structure, but it also has this extra multiplication on it, okay, which is this Lie bracket. This turns out to be a non-associative Lie bracket. Okay, now I mentioned this is the Lie algebra. I haven't defined what a Lie algebra is. Okay, and in some ways it's because you don't need to. Okay, if you're willing to work with the universal enveloping algebra, in which some ways is more natural, you can dispense with the definition of the Lie algebra. Okay, but just in case you're interested as to roughly what a Lie algebra structure is, okay, it's going to be an algebra in the sense that it's going to be a vector space over a corresponding field. So here we're working over the reals, so a vector space over the reals. And you want on it some sort of a multiplication. And the first thing you should realize is that if you reverse the order of these two, okay, so what happens? So when you look at the corresponding differential operators, the terms get swapped, so it goes to its negatives. So that means that this negates. Okay, so it's skew symmetric in that sense, or anti-symmetric. So Lie algebra always has a multiplication which is skew symmetric. Okay, it's bilinear, of course, over R. And the other thing is that even though it's not associative, it carries with it an analog of the associativity, which involves the various triple products, and that's called the Jacobi identity. Okay, so we won't define what a Lie algebra is. We'll just say this is the Lie algebra. It has this multiplication, and that's partly because we can deal instead with the universal enveloping algebra here. Okay, so now we can answer the question that I raised initially. Okay, if you look at this universal enveloping algebra of G, of course it is an R algebra, and it's generated by this Lie algebra Gothic G here. And what are the relations? What you do is you look at all these elements A and B inside here, and you set AB minus BA, this commutator, equal to the Lie bracket of A and B. Okay, so this thing, which looks like a quadratic term here, gets identified with this. This will be a degree 1 term, so to speak, inside G. Okay, and that gives you a complete description of this universal enveloping algebra of that Lie algebra. So let's do a simple example. I won't do it completely, but it's not difficult. Let's consider G, the Lie group GLNR of invertible real n by n matrices. And in this case here, this is an open subset of the set of n by n matrices. So its tangent space, which we denote by Gothic GLN, is just the set of all n by n real matrices. Okay. And so let's have a look at an element here, A, inside here. So that gives you a corresponding left invariant vector field, XA, and that gives you a differential operator, which is also left invariant. Just to remind you, if you have a function on this group, so let's say B is your variable element on your group, then what do you do? Well, you can hit this group element with e to the ta, where t is just a real parameter. You evaluate the function here, and you differentiate this as you vary t with respect to t, and you look at the value when t equals 0. Because when t equals 0, this is the identity, so it kind of corresponds to at b. Okay, and that gives you a new function. Okay, and that's the differential operator. So here you want to look at, well, there is some Lie bracket on this Lie algebra. Okay, and it's going to be skew symmetric. And it's going to be, of course, bilinear, okay, of the reals. And you can ask, what is this? So this has to be some other element of this Lie algebra. So it has to be an n by n matrix. And if you think about it, well, it's got to be skew commutative, and it's got to use the matrix multiplication, because that's the group structure that you have here, okay? They're the only things that you can use. And so it's very natural to guess this as the answer, and in fact this is the answer as to what this Lie bracket of these two n by n matrices is. It's just the usual commutator, AB minus BA. Okay, and so that gives you here the Lie bracket. So here AB minus BA, so here this is defined inside, so this is going to hold inside the universal enveloping algebra. But this right-hand side is defined using matrix multiplication. It's the matrix product of A and B minus B times A. So this is going on inside this algebra here, which is quite a bit smaller than the universal enveloping algebra of this here. Okay, but it will have this relation. Universal enveloping algebra will still have this relation here. Okay, so what I said is that this Lie algebra is supposed to represent locally at a point the group structure of a Lie group. And the best way to see that is using this wonderful formula by Campbell, Baker, and Hausdorff. So this is called the Campbell, Baker, Hausdorff formula. Okay, and it goes as follows. So we're going to consider A and B are going to be small, okay, elements of the Lie algebra. Now remember, the exponential map is a local diffeomorphism. It's a local diffeomorphism between the tangent space, G, as in the neighbourhood of 0, and the neighbourhood of the identity on the Lie group. Okay, so let's just see what happens when you try to multiply two elements, exponential of A and exponential of B together. Okay, so in some neighbourhood, if A and B are small, okay, this is going to give you some isomorphism. So here's your tangent space, G, and you have some exponential map down to your group. This is 0, this is 1. So if A and B are small, they're in some small neighbourhood, and you can assume that that's in some neighbourhood which is diffeomorphic to a neighbourhood of 1 in the Lie group. And you can say, well, is that the exponential of something coming up from above? And what is it? How do I work out this product using information in the Lie algebra? Okay, so that's the question. Well, the answer is there's an explicit formula. I've only written out the first bit, but it goes on for infinitely. Okay, so if you were to look at this as just numbers, a times xb, of course, it's just the exponential of a plus b. But in general, hopefully you realize that for matrices even, okay, exponential of a times the exponential of b is not exponential of a plus b. If you just looked at the exponential of a plus b, okay, that is commutative in a and b. Whilst if a and b don't commute, then exponential of a and exponential of b don't commute, so you can't swap the order of these two. So you might expect that the commutator should come in. And in fact, the commutator does come in. Okay, and it turns out that you can modify the formula, usual formula, exponential of a plus b, with all these commutator or Lie bracket terms. Okay, so the first Lie bracket term involves just a Lie bracket of two things, half a Lie bracket b. And then there are higher order correction terms. There's a third order correction term, so that's for the triple brackets. Okay. By the way, if you have three a's or three b's, you'll get 0 because the Lie bracket of a and a, right, is equal to 0. So you can only get a Lie bracket b or b b a. Okay, you have to add a 12th of each of these. So they're the third order Lie brackets. And then there are fourth order, fifth order, and higher order ones. And this is a really wonderful result, which basically tells you what's the upshot of this. Okay, so remember the vector space G. Okay, this is tangent space. So manifold theory kind of tells you that this G, the group, is locally, from a topological standpoint, like this Gothic G, the Lie algebra. But if you want to know, oh, how do you multiply two things which are in a small neighbourhood of the identity here? In other words, multiply xa and xb if a and b are small. How do you multiply them? Well, you can get that just using this Lie algebra structure, because this expression here just uses the Lie bracket. It's pretty neat, huh? Okay, so it's in that sense that the Lie algebra really tells you how to multiply, at least locally, in a neighbourhood of 1. So this is a wonderful formula, and I just wanted to start you off on the calculation. It's not so easy to prove this, but to see why something like this might be true, if you do the following heuristic calculation, that will tell you that, oh, yeah, maybe this might be true. Okay, so let's just expand these two. Okay, and you can do this, I guess, let's just do it. Probably the easiest thing is to think of it in terms of matrices. Okay, so let's look at the exponential of a times the exponential of b. Exponential of a, if you look at for matrices, so here a and b are inside GLN. And then when you take the exponential, we saw before that this is just the usual exponential formula given by the usual power series. And then you can multiply these terms together. Okay, so we'll do it as a power series. So we go from lower order to higher order. So 1 times 1 gives you 1, the constant term. There's an a times 1 and b times 1 gives you the linear terms, a plus b. And the square terms are, there's a half a squared times 1. There's an a times b. And there's a half b squared times this one, which is here. So that's a quadratic term. And all the other terms are higher order. And as you can see here, remember you have an AB, and that doesn't necessarily equal BA. Okay, so that's one of the reasons why it's tricky to get the usual formula. In fact, you can't get it. Okay, but let's have a look here. So I claim that this quadratic part you can rewrite as half of a plus b squared plus half times the commutator of a and b. And why is that? When you expand this out, remember a and b don't commute. So when you expand this square out, what do you get? You get half a squared plus half ab plus half ba plus half b squared. So you see, you don't get an AB, like as if like when they commute. Okay, if A and B commute, then you'll get an AB because you can add these two terms together, but they don't. But what happens is that if you throw in this half the commutator, you'll get plus half AB, which adds to this half AB here to give you your AB, and you have a minus half BA, which cancels off this other term. So that's why these two terms are the same. And I hope you can see that if you look at the exponential on this side, right? How do you form the exponential? You do 1, and then you do add this plus AB, and then you have to add half A plus B squared. And the point is that half A plus B squared, it's not giving you the right answer. It doesn't give you this AB, it gives you half AB plus half BA, right? So to correct it, what do you do? To correct it, we're going to throw in this plus half the commutator of A and B. So we throw in this term. So when you do exponential of these three things now, okay, you'll not only get all the terms that you see here up to the quadratic, but when you do the linear term for this one, you'll throw this in as well, which just fixes up this non-commutative problem here. And that gives us a wonderful Campbell-Baker-Hausdorff formula, which in turn shows us how the Lie algebra structure, so this extra Lie bracket, okay, captures locally the group structure of a Lie group near the identity. I hope you enjoyed this adventure in pure mathematics.